Yes. Okay. I think we are to. How many students are logged? There is right now. We wait for a few minutes to plug in the students. We have to wait for it. Okay. Only one. I think it is 3 minutes. Okay, we have to wait for more 2 minutes. Yeah. Okay. Here in more there is disadvantages. Okay. So today in previous good morning everyone. Today we have discussed about the second chapter, elasticity. Okay. Before starting the elasticity, we have finished the first chapter, mechanics. In that mechanics, we have learned successfully the compound pendulum, its uh, procedure, how to perform the experiment. After that, Catter's pendulum. Catter's pendulum also, it's if you have to reverse it and calculate the time period to equal to, right, as you know. And practically also we have that experiment in practical purpose. Okay, for 100 marks in practical. After that, gravitational potential at point inside, outside the solid sphere, hollow sphere. All those articles we have learned in chapter first in mechanics. So today we have uh, start the elasticity. Okay, as you know that what is elasticity? What is elasticity? I want to uh, know from your side. What is elasticity? Yeah. What is elasticity? Yeah. Yes. In physics, okay. Elasticity can be defined as very simple way. The force applied. What? The force applied to a body can produce a change in shape or size or both. Okay. In shape and size of the body. Such a change is called as deformation. Okay. For example, we have to uh, take the example number of practical day-to-day life examples. If we have to take the rubber and apply the force, it is stretch. All right. Then what? when we are to apply the force, then it extends or change in length, right? Is size and shape change. That one is a good example of elasticity. Okay. And in a scientific way, how we are to define it? Elasticity is the property possessed by a material body. What? Material body by virtue of which it regain its original condition when the applied deformation force is removed. So I already have given the very simple example that which example? Deformation force, right? Rubber. If you have to take the rubber and apply the force on it, then what happen? Its size and shape changes. Its change in length is taking place. If I remove the applied force, then it come to the its original force. Sorry, original size. That means what? Applied force. That one is if I remove it, then it gain its original shape and size. Okay. When we apply the force, then what happen? That applied force is called deformation force. Okay. And when I remove that deformation force, then again that rubber, whatever maybe we have to take in hand, that come to its original length, size, and shape. Okay. So this one is this what? Elasticity. Okay. What happened? The internal restoring force per unit area is called stress. What is stress? Stress is nothing but the internal restoring force per unit area is called as a stress, and its unit is Newton per meter square. Okay. So these are the very simple basic definition of this elasticity. Okay. And after that, how we can define this stress? The stress can be defined as what? Internal restoring force. Which one? Internal restoring force. Okay. Restoring force. Okay. Okay. Internal restoring force. That's good. Okay. If the internal restoring force per unit area is called what? Stress. Internal restoring force is called as stress. So after that, how I will explain, how I will change the another term which is called as strain. The change in dimension per unit original dimension is called as strain. Okay. The change in dimension per unit original dimension. If I apply the force on particular material, elastic material, particularly rubber, then what happen? That change in dimension is taking place when I apply the force on that surface. And that is called as a strain. What? Strain. So you know that if according to Hooke's law, what is it? Within the elastic limit, stress is directly proportional to the strain. So modulus of elasticity is what? Modulus of elasticity is equal to stress. Okay. As you know, the stress is what? Stress is the internal restoring force per unit area, right? Per unit area is called a stress, and the strain is what? The change in dimension per unit original dimension is called strain. The change in dimension per unit original dimension is called a strain. So if uh, I use the Hooke's law, then using that Hooke's law, we can write the uh, we can write the we can write the modulus of elasticity. So modulus of elasticity is nothing but the ratio of stress to strain. Okay. So what is it? The stress divided by strain. Okay. And the unit is modulus of elasticity is Newton per meter square. For MCQ, might be question asked in exam. The modulus of elasticity SI unit is Newton meter square, Newton meter cube, okay, centimeter Newton centimeter square, Newton per centimeter cube, and none of these. Okay, like that. And for CGS unit, dynes per centimeter square. Okay. So keep in mind small articles and questions related to that. Okay. Uh, as you know that, as per our syllabus, for elasticity, first of all, modulus of elasticity, that one is elastic constant we have. Another article is, next article is twisting couple on a cylinder, bending of beam or bending moment. Okay. Next one is curvature of a beam or bar. Okay. Uh, and another one, cantilever loaded at free end. Okay. In this, there are two derivations. Cantilever loaded at free end, cantilever loaded at free end. For that, sorry, I have some uh, issues with this because uh, there is some erasers we can use. Okay, good. Then I will regain its highlighter or pen. I take this pen as it is. Okay, can we use? Okay, good. So for second derivation, first one is when weight of beam is ineffective. This carries 10 mark, right? Derive an expression of cantilever loaded at a free end when weight of beam is ineffective and when weight of beam is effective. Both carries 10 marks. Okay, for derivations. Next thing is that, and last derivation is depression of beam supported at center. This one is at center. Okay, that's it. Good. So this one is our proposed syllabus for chapter second, elasticity. As you know that already we have discussed. Once I repeat this, what is a stress? What is elasticity? Elasticity means what? The force applied on a body can produce a change in shape or size or both in shape and size of the body. Such change is called a as deformation. Okay. And if you are to say the elasticity is what? The elasticity is nothing but the property possessed by a material body by virtue of which it regain its original condition when the deforming force are removed. That one is the elasticity. And for stress, the internal rest, internal restoring force per unit area is called a stress. And how we can define this strain? The change in dimension. The change in dimensions per unit original dimension is called strain. And using the Hooke's law, if I apply the Hooke's law, then how that changes? The modulus of elasticity can be defined the ratio of stress to strain. Okay. Very simple way. First of all, we have learn what is elasticity. Elasticity is the property of material body by virtue of its size and shape can change when we apply the force, and that force is called as deformation force because when we applied that force, the body is deformed, right? Its size and shape changes. That's why it is called as deforming force. When we remove that deforming force on it surface, then it again gain its original shape and size itself. That's what. Okay. And after that, a stress, the internal restoring force per unit area is called a stress. And strain is the change in dimension per unit original dimension is called as strain. And using Hooke's law, the modulus of elasticity, which is equal to stress upon strain. Okay, good. You understand very well. I know. After that, we have to take the another article, which one is our first article as per our syllabus? That one is elastic constant. This one. Okay, this one. Elastic constant. So what is elastic constant? Okay. The modulus of elasticity is material property. What is it? Material property, which describe its stiffness, its hardness, and is therefore uh, one of the most important properties of solid material. Okay. So the mechanical deformation puts energy into a material. Okay. The energy stored elastically or dissipated plastically. Okay. The way of a material stores uh, their energy is summarized stress and strain. Okay. In elastic case, what happen? In elasticity, the material is possessed its energy in the form of stress and strain. Okay, stress and strain. So what is already we have know the definition of stress. Stress is what? The force per unit area, and strain is, yes, elongation. Stress is what? Elongation. Elongation means what? If I have applied the force on, for example, we have to take the sponge, right? Sponge duster. We have applied the force on that surface. What happen? Its size changes. If I remove the force, then regain its original size and shape. Okay, that applied force is I mentioned is what? It is deforming force. Okay, and strain is what? Strain is elongation. Okay, if I already have given the example, if you have to take the example, very simple, uh, uh, that rubber example. Okay, if I apply the force on it, then what happen? The uh, when apply the deforming force, then its length changes when I apply the force, and if apply force, then elongation is taking place. Its change in length is taking place. Okay, that's it. And that is the elongation which we can say. Okay. And that elongation at which extent is taking place, that one is per unit length. Okay. The stress is defined as force per unit area. And strain is what? Elongation. Very simple. Okay. So, using Hooke's law or elasticity of modulus of elasticity, stress upon strain. Stress what? Stress is this one. Okay. What? Stress is this one. Stress is defined force per unit area, and the strain is what? Strain is elongation. Okay. Or conformation per unit length, whatever may be it. Okay. So very simple way you can define it. Okay. So modulus of elasticity, what? Elasticity. How I will write here? Elasticity. Stress. Okay. Stress upon strain. That's it. Already we have this equation. Okay. Not necessary to mention here. So very simple way you understand this one. Okay. Next is what? Young's modulus. That one is elastic constant. Okay. When a material deforms elastically, the amount of deformation likewise depend on size and size of the material, but strain for a given stress is always the same, and two are related by Hooke's law. Okay, that's it. Okay. So next is what? We have to take the Young's modulus. Moduli of elasticity or elastic constant, just you have express what is stress and what is strain. Okay. And after that, modulus of elasticity, which is equal to stress upon strain. Mention that equations. Okay. That's it. In elastic constant, what? Elasticity equal to stress upon strain. First of all, you define strain, after that strain. That's it. And after that, uh, we have to take another one. Okay, that one is uh, modulus of Young's modulus. Okay, For Young's modulus, okay, for Young's modulus, within the elastic limit, okay, what is Young's modulus? What is Young's modulus? Okay, what is it? Young's modulus? Yes, Young's modulus, y, within the elastic limit. What is elastic limit? If I take the rubber, okay, apply the force, and after certain limit, that is the limit. If I apply again force, then it what? It may be beyond the limit, and its result is that it split into two parts. Okay, fragments. So elastic material have particular limit to bear the applied force. Okay. So like this, what happened? What is? That's why it here used the word which one? Elastic limit. Within the elastic limit means the bearing capacity of force for a particular material. Okay. That is the within the elastic limit, which we can say. So what is it? It is the ratio of longitudinal stress. What? Longitudinal stress, okay, longitudinal stress to longitudinal strain, longitudinal strain, okay. What is it? What is it? Yes, longitudinal stress divided by longitudinal strain. Again, Young's modulus is what? Longitudinal stress and longitudinal strain. Young's modulus is nothing but the ratio of longitudinal stress to the longitudinal strain. Okay, very simple way, as you know that the definition of stress, right? Okay, and what is the definition of strain? Okay, again I will remind you what is the stress. The internal restoring force per unit area is called as stress, and strain is what? The change in dimension per unit original dimension is called as strain. So for Young's modulus, within the elastic limit, we can define the ratio of longitudinal stress to longitudinal strain. Good. So this one is the y. Y is the what? Young's modulus. Okay. Y is what? Young's modulus is equal to what? Longitudinal stress divided by longitudinal strain. Okay. For derivation purpose, we if you are to consider the material, which material? Metallic wire, if you are to consider this one, and this one is support, rigid support, then this one is upper, this one is rigid support, and this one is the metallic what? Metallic wire, which we have considered. Okay. So what happened? Its original length is what? Capital L, this much. Okay, this much. Okay, capital L, original length is. And how the radius is, how that radius is from this to this portion. Okay, that radius R, okay, suspended from its rigid support. This one is what? This one is a rigid support. It's a rigid support. Okay. So we are to discuss, consider this material. We are to take on the first metallic wire. Okay, this one. Okay, and which possesses or which have the length capital L. After that, it have the particular radius. Okay, this radius. Okay, R, and we have to discuss more about it. If you are to consider this metallic wire, this have the particular mass M. Okay, capital M. Okay, capital M mass of the metallic wire. Okay, we have to consider here that the mass of the, just moment, huh? Okay, here mass of the metallic wire. Okay, okay, mass of the metallic wire M, and another is here mass which is attached to free end of the wire, and if I increased the length, then this one is the dotted portion. Okay, at which rate that length is increased from its free end. Okay, then a equal to pi r square. Okay, that one is the case. Okay, so what happened? Longitudinal strain, change in length. Longitudinal strain means what? Yes, longitudinal strain, change in, yes, longitudinal strain means what? First of all, you have to take change longitudinal strain. Strain is what? Yeah, change in length. Strain applied per unit area. Okay, per unit length. Okay, so change in length divided by original length. Okay, in our case, what is it? Once I here draw this figure very simple way. This one is the rigid support. Okay, and here this one is the our bar. All right, like this one. Okay, this you have the length L. Okay, from this point to this. Okay, up to here we can take here. Okay, up to here we have to take the bar. Okay, what happened in this case? This one is the R which we have considered. Okay, R is the radius of this material. Okay, bar, material bar. This one is the rigid support, and this suspended to the rigid support. Okay, what happened if I applied the force? Okay, this one is the change in length, small l. This one already figure is here. Okay, small length here, this one. Okay, and after that, here we have applied the mass, attached mass. If I apply the mass here, attach the mass here somewhat, all right, then capital M mass, attached mass, then this change in length is taking place from here to here. Then what happen? Change in length, this small l, all right, this one. Okay, this one. Okay, okay, here small l divided by original length is this much length, original is this. Okay, this one. Good. After that, this one is for longitudinal strain. Okay, what is our formula for Young's modulus? Yes, for Young's modulus, y equal to, yeah, this one, longitudinal stress upon longitudinal strain. Okay, so you have defined the longitudinal strain. Okay, after that, longitudinal strain, what is it? Applied force. Applied force is what? We have applied the force on mass attached to this wire, right? M into acceleration due to gravity acting on it. Okay, so how I will write here? M G divided by area of the cross section. Area of the cross section over here is pi r square. This one. Okay, this one. Okay, A equal to pi r square. That's it. Okay, A equal to pi r square. That's it. So this one is the what? Stress, longitudinal stress. Longitudinal stress is which is equal to applied force. Applied force is we have M. Okay. After that, the acceleration due to gravity acting on it divided by what? Up area of cross section pi r square. That's it. Okay. So this one is the stress. Okay. And after that, uh, I want to put this term, which one? Longitudinal strain and longitudinal stress in Young's modulus. So how I will write the Young's modulus? I will write the Young's modulus like this. How? Longitudinal stress. Put this value, longitudinal stress, divided by which one? Longitudinal strain. Longitudinal strain is what? Yes, L divided by original L. L deformed length, right? After original length. Okay. So that one is the stress divided by strain. Okay. This one is the stress, this one is the strain, and this one is the Y, Young's modulus formula. Longitudinal stress, the ratio of longitudinal stress to the ratio of longitudinal strain. So stress divided by strain we have. Okay. And Young's modulus we have. How we have to write Young's modulus? Young's modulus we have simply write, simple way we can write Young's modulus, which is equal to m mass of the wire, which we have considered for experimental purpose or theoretical purpose to verify its elasticity. So m into acceleration due to gravity g, right? Okay, here m acceleration due to gravity into original length of the metallic wire divided by area of cross section which we have considered, right? This area pi r square, okay, into which factor L, change in length. Okay, this one is the y. What is it? Y equal to. Okay, that's it. And we have finished this Young's modulus. Young's modulus is defined as, once I repeat it, Young's modulus is defined as the change in longitudinal stress to the change in longitudinal strain. Okay. For strain, we have L divided by L, small l divided by change in length divided by original length. So for longitudinal stress, applied force M into G divided by area of cross section. Okay, put these values, and we have obtained the Young's modulus, which is equal to longitudinal stress divided by longitudinal strain. Put these mathematical values mg divided by pi r square divided by L divided by L, and right, we have derived this equation with this equation. Okay, y equal to, right, Young's modulus equal to mgl mgl. Oh, sorry. I think there is. I will take eraser. There is some unwanted things. Okay. Right now it's okay. 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 So Young's modulus, you understand? I think so. Okay. This y equal to capital E to G. That's good. Okay. After that, I think, is it possible to bulk modulus? I think yes. We have one more article we have might be in process to finish. We can, yes, we can finish it very simple way. Bulk modulus. Okay. For bulk modulus K. Okay. What is bulk modulus? What is bulk modulus? Bulk modulus is within the elastic limit. Same as in previous case for Young's modulus, within the elastic limit. This one. Okay. Same way here also, within the elastic limit. Whatever maybe we have to done, perform, is within the elastic limit. Okay. So for within the elastic limit, okay, it is the ratio of bulk stress. What is it? Bulk stress. What is it? Bulk stress divided by bulk strain. Okay. Instead of longitudinal, you have to use the word bulk. Just keep in mind. Stress divided by strain. Here. Here you have to see here. Here. Stress divided by strain here. Okay. Stress divided by strain. Okay. Here is some corrections. I think so. Here this one. Okay, good. So what happened in this case? What happened in this case? Young's modulus, longitudinal stress divided by longitudinal strain. Okay. For bulk modulus, we have to use only bulk, right? Bulk modulus, bulk stress divided by bulk strain, as it is. Just you have to use the bulk modulus K equal to, right? K equal to bulk stress divided by bulk strain. Okay, okay. So for this, we have to consider a spherical body of original volume, right? Phi. If you have to consider this body, complete body, right? Which have the volume phi, right? Already here mentioned this one. Then we have applied the some force, normal force F, if you are to acting on all side, then what happen? What happen? Yes, if I apply equal force on all side, normal force, then what happen? There is change in volume taking place, right? The change in volume is taking place. Okay. If I apply the force on all side of that spherical body, then what happen? Its change in volume is taking place. Okay. And that change in volume, okay, this one, change in volume, that one is V into dV, right? Okay. Change in volume is what? dV. Okay. Yeah, dV. That's it. Change in volume at small extent. Okay. Its original spherical shape is changed and it become this small one. And that one is V into dV as shown in this figure. Okay. So what happened in this case? Let A be the area of body. Okay. If I consider A be the area surface of the body, then bulk strain, how I will define the bulk strain? For bulk strain, change in volume divided by original volume. Change in volume is which one? Change in volume is dV, right? Okay, so I have written here dV as it is, divided by original volume is V. So how I will write it? Change in volume divided by original volume. Okay, that one is bulk strain. Okay, bulk strain. So what is this? Bulk strain I have defined. Okay. Same way, I will define the bulk stress. For bulk stress, how? Bulk stress here. How I will write? Applied force upon area of cross section. Applied force is F. Okay. And area of cross section, right? Area of cross section. Okay. E. Area of cross section, which we have E. Okay. Force F. Okay. Force divided by A. Okay. That's it. So bulk stress is how I will define uh, bulk modulus. This one is bulk stress. This one is what? Bulk stress. And bulk strain is what? dV by V. So put, therefore, the bulk modulus can be defined as bulk stress to strain. Stress to strain, put these values, right? Okay. Here this one. Okay. Here put these values and you got the bulk, what is it? Bulk modulus K. Okay. Here bulk modulus K, which is equal to bulk stress upon strain. Okay. Here this one, stress, bulk stress upon bulk strain, bulk strain. That's it. Okay. I think there is time limitation, and I think our time is finished. Okay. And thank you, all of you, and you have a wonderful day for your uh, continuous attention in this lecture. And you have a great day. Thank you, and have a wonderful day ahead.